Hello, physics students. In this short video, I want to take you through how to solve conservation of momentum problems. I'm going to ask you take out your notes and follow along with some of the examples. We'll be going through a few examples to help you understand the best way to approach conservation of momentum. Thanks. Please reach out if you have any questions. Have a great day. The first thing I'd like to talk through is a little bit of a review. Impulse and momentum work really closely together. As you know, impulse is the force applied over a given amount of time, and momentum is the mass times the velocity. The unit for momentum is a kilogram times a meter per second, and this key relationship right here, where the impulse is equal to the change in momentum. So the longer you apply a force or the greater force you apply over a certain amount of time is equal to the change in momentum, the mass times the velocity. We can rewrite that equation right here. Force times time, or the impulse, is equal to the final momentum minus the initial momentum. Remember, our subscripts F and I refer to the final and the initial momentums. All right, further expanding on these ideas, if we have, let's say, a hockey puck that has a mass of 0.115 kilograms, and a player takes a shot and it exerts a force of 31 newtons for 0.15 seconds, could we figure out how fast the puck would be moving with our impulse and momentum? Turns out, yes, we sure can. Start by writing out the equation. Impulse, so force times the change in time, is equal to the change in momentum. The mass times the final velocity minus the mass times the initial velocity. Then we can take a close look at adding our numbers in. The force is 31 newtons. The time is 0.15 seconds. The mass of the puck is 0.115 kilograms. We're solving for the final velocity, so you see that listed here. The initial velocity is 0. So this term will actually drop out of our equation. If we simplify a little bit farther, we have multiplying 31 times 0.15, 4.65, and multiplying 0.115 kilograms times final velocity gives us 0.15 times final velocity. Now I can divide both sides by that 0.115, and I'm going to end up with about 40.43 meters per second for my final velocity. Keep in mind that this was using our impulse and momentum equation. This is a good review. We'll be coming back to these ideas. All right, so what is conservation of momentum? Well, momentum is conserved, meaning that momentum can't be created or destroyed. And in fact, this is one of the fundamental tenets of physics and all the observations that we've been able to make as scientists throughout all the years. Conservation of momentum has never been proven otherwise. So even when we look at rockets, the momentum has to be conserved. The velocity of the rocket and its payload is determined by the mass and the velocity of the expelled gases. So we can't create or destroy any momentum, even in a rocket launch. On a simpler idea, let's take a look at a cannon. And when we take a look at a cannon and a cannonball, this is the system that we're going to be investigating. And when a cannonball is fired out of a cannon, we know that there's recoil, so the cannon gets pushed back. But a question naturally arises is why, if the momentum is the same, why does the cannon only move backwards a little bit and the cannonball moves forwards a lot, right? I mean, it has a high velocity. Well, that can be explained with what momentum is. It's the mass times the velocity. So for the cannon, you have a much greater, much larger mass, and for that same to produce the same momentum, therefore it would need a much smaller, much less velocity. Similarly, the cannonball has a less mass, right? So much smaller than the cannon. Therefore, it would have a much greater velocity to produce the same amount of momentum. Remember, momentum is the product of mass and velocity. So this concept is going to come across a lot in our examples and a lot of the concepts that you'll be looking at. Just remember that momentum is not equal to velocity, and if you have a greater mass for the same momentum, the velocity will be far less, like in the case of the cannon in terms of this problem. All this is going to relate to conservation of energy. But before we get into the equations, we really have to think about notation. If we have masses, like here we have mass A and mass B, and they hit each other. So you see in the before situation, before they're sliding towards each other, they're going to meet somewhere in the middle. Well, we need to keep track of what's happening. So we're going to use this I to stand for initial. So this would be the velocity of block A initially, the velocity of block B initially. Just keep track of those little subscripts, and all these equations are going to make a lot more sense. After the collision, we also have to keep track of that amount of momentum. And so we're going to have to list the velocity of block A, and F is final, and the velocity of block B, and F is final. So we're going to use the initial and the final to help us determine before and after. All right, how does that all fit in? Well, the law of conservation of momentum is closely tied with the law of conservation of energy. But when we talk about the total momentum of a closed system, it does not change, okay? So the initial mass and velocity of block A plus the initial mass and velocity of block B is equal to the final or after velocity of momentum of block A and the momentum of block B. Always true, the total momentum before is equal to the total momentum after. And we can simplify because momentum is symbolized by a lowercase p. So the momentum of A plus the momentum of B initially is equal to the momentum of object A and the momentum of object B finally. Okay, now how does this work in an equation? Well, let's take a look. So in this example, we're going to take a look at what this looks like when we substitute numbers in. So notice on the diagrams at the bottom, I have a before case and I have an after case. So these blocks are going to hit. One of them has a bigger velocity arrow than the other, and afterwards, one of them has a bigger velocity arrow than the other. So when we look at how this sets up in an equation, we need to keep track of our masses, mass A and mass B, and our initial velocity of block A and block B, and our after. So we're going to solve for how fast is block B moving after the collision. Our conservation of momentum equation will help us set that up. So the initial momentum of A and B added together is equal to the final momentum of A and B added together. I'm going to substitute in what I know, and it looks like from our givens below that we have a 12 is our mass for A, 18 is our mass for B, and so I'm going to say those in both those places. Now we just substitute in our velocities. 4 is our initial velocity for A, -8, and momentum does have a direction. Notice it's moving to the left, so we have to keep that in mind. So be careful with your signs for momentum. And then notice the 11 meters per second is also negative because it's moving to the left. And then we're going to solve for a positive final velocity because it's moving to the right. All right, I'm going to move this so you can see some of these numbers. I'm just simplifying, and you end up with a velocity to the right of about 2 meters per second. Okay, let's take a look at another example. All right, in this next example, we're going to take a look at conservation of momentum again with a slightly different angle. All right, we have an arrow that's been flying through the air, and it hits a block of wood that's at rest, and they become stuck together, and they both move with a final velocity of 1.2 meters per second. Now, when you look at these problems, we're still going to use the same conservation momentum equation. Momentum before of the block and the arrow equals momentum after of the block and the arrow. But we have to take a look a little bit at what those velocities are in this case and check our units. Hopefully you can see in this chart that I've already done a conversion. We have to make sure the units match before we do any of the math. So I've changed kilogram or grams into kilograms for the arrow, and now everything's consistent. Also in the chart, notice that the final velocity of the arrow and the final velocity of the block are the same. They say they become stuck together. So look for those clues when you're reading through these problems. All right, I'm just going to show you the math now. I'm substituting in what I know for both the arrow and the block initially. Notice that there is a 0 velocity here, so that term will drop out. And I know that the arrow's momentum and the block's momentum at the end. and I'm using the same velocity because they're stuck together. Okay, now I'm just going to show you the quick math and substitution of this. Just plugging that in, I should get a arrow initial velocity of 241.2 meters per second. Great. Okay, another block and arrow problem, and I actually have one more after this, so just get ready. All right, again, we have to double check our units. I've converted, that's great. But here it says that the arrow bounces off and has its own velocity in the opposite direction. I see the negative sign, that's really important. So when I substitute the numbers in this time, I'm going to put in my initial velocity of the arrow, the initial velocity of the block, and I'm also going to make sure that I have a final velocity of an arrow that's different than the final velocity of the block that we're solving for. All right, so be careful with that for this problem. Substituting and solving, I get a block velocity of about 1.356. Please double check your work and see if it matches. All right, here we go. Last problem, arrow and block number 3. And again, same idea of conservation of momentum, but this time the arrow actually gets to fly through the block of wood and it leaves at a velocity of 198 meters per second. How fast will the block of wood move? Again, making sure units match first, and then we can substitute in what we know. I'm going to look at the momentum of the arrow with its velocity and mass plus the momentum of the block. It starts from rest, so that's 0, is equal to the momentum of the arrow after the collision and its new velocity and the momentum of the block and its new velocity. Notice that the positive in this case, there's a positive 198 because it's moving in the same direction as the block after they collide. All right, let's take a look, and we end up with a block velocity of about 0.216 meters per second. Hopefully this makes sense. Like I said, please reach out if you have any questions, and we'll talk through any of those in Schoology. Thanks again, and have a great day.